All right. Well, it is 9 o'clock my time, and I know a variety of other times where everybody else is, but we want to be conscious of everybody's time today. So we will get started. And as other people join, I'm going to turn off the microphones and cameras for everybody just so we don't get feedback. But I wanted to thank you all for joining us today. And I wanted to thank Ken for his presentation. If you have questions, put them in the chat. And I'm going to turn this over to Jennifer Clemens, who's going to do the introduction for Create. But once again, thank you, everybody, and happy Friday.
Hi, everyone. So welcome to our final webinar of the spring series. I am Jennifer Clemens, one of the senior personnel for the Create Energy group. Today, our webinar is on low-cost gas law demonstration using Arduino. I'm super excited to hear this presentation because I worked with Ken for many years, and he was a really early adopter of the Raspberry Pi Arduino controllers, and he always likes to tinker, so he was always coming up with new things. So if you don't know about us, please take a look at our website, createenergy.org, and sign up for our newsletters. So you'll get opportunities like these webinars and also some of the workshops that we do in the summer. And there's a whole lot of curriculum and educational resources that are available there for anyone for free. Our next upcoming event really is High Tech. So most of us will be at the High Tech conference in Minneapolis the end of July. So I know there are some energy special interest groups and some energy talks at that event as well. So today our presenter is Kenneth Mecham. It is my pleasure to introduce him today for our final webinar in the spring series. I've known Ken for nearly 14 years, where I worked with him at Delaware Technical Community College. He was one of the founding members of our energy management program at Delaware Tech. But education was really his third career. He started Delaware Tech 3 days after retiring from a career in the public sector, where he managed public utilities in both Delaware and Arizona. But Ken was never good at retiring. Even after he left full-time instruction, he kept coming back as an adjunct. And usually about a year after he said this was my last class, he would come back and say, you know, I got some things I'd like to try. Or I'd give him a call and say, hey, you know, an instructor is out for a little bit. Can you help cover? And he always would help cover for us. Prior to that, he owned his own electrical and mechanical contracting business in Virginia for over 20 years. Ken always liked to say he has 4 master's degrees. He has a master's degree in economics, but he's also a master electrician, a master plumber, and a master HVAC tech. Ken is married with 5 children, 14 grandchildren, and 8 great-grandchildren. He and his wife, Linda, live just north of Lewis in Delaware. And hopefully this latest retirement might just have stuck, because every time I talk to Ken and Linda are too busy to work, often traveling the world and visiting all of those family members. So I'd like to welcome Ken and let him take over the controls.
Well, thank you, Dr. Clemens, for that kind introduction. And thank you to Create for this opportunity to share this demonstration with you. And thank you for each one of you that are in attendance. So we will just jump right in here with the presentation. And we're going to be talking about a low-cost way to show the gas laws. And our agenda for today includes just a summary of a project in a minute. We're going to gather all the parts together and put them together. And then we're going to look at the Arduino sketch or program. We're going to visualize the Charles and Boyle's law, and then continue on with the Gay-Lussac law and add data logging to our project. We'll go just one step farther with some atmospheric pressure and altitude measurements, and then some final tips and takeaways along with maybe some questions. So here's our 1-minute summary.
I had tried to use 2-liter soda bottles to show the relationship between pressure, volume, temperature in the gas laws. I came upon the idea of using the Arduino microprocessor chip along with a pressure sensor that I could insert inside a 2-liter soda bottle. Programmed with the Arduino microprocessor, one could see the response of decreasing the volume of the bottle by squeezing it. The pressure would increase as the volume decreased. Also, the relationship with regard to temperature. By using a hair dryer, we're able to heat the soda bottle, raising the temperature and consequently raising the pressure while the volume stayed basically the same.
Okay, that's our 1-minute summary. So let's gather the parts and put them all together. First off, we're going to need a plastic bottle, our BPM 280 pressure sensor that's in the circle, some 4-conductor wire, some male and female conductors, some heat shrink tubing. We will be using a LCD shield on top of our Arduino Uno microprocessing board. Our tools will be a hot glue gun, a soldering station. We'll need a drill to drill the hole in our plastic bottle, a drill bit, our wire strippers, and a heat source for our heat shrink tubing. We'll begin the process by drilling our hole in the bottle at the end and inserting the wire through it. At the end up here, we will go ahead and attach the connectors, put on the heat shrink tubing, and a great big old glob of hot glue at the very end of it. The purpose of the hot glue is to try and prevent air passage through the conductor as we change the pressure in the bottle. We're going to attach the BMP280, which is the digital atmospheric pressure temperature sensor. Really inexpensive but highly accurate. Where the arrow is pointing is actually where the pressure sensor itself is. It's a piezo-resistive strain gauge, and as the atmospheric pressure changes, it will allow us to measure that difference. We're going to attach that then to the wires that we prepared earlier, and we're going to pull that wire now back into the bottle, and we're going to seal it where it came out of the bottle once again with our hot glue. It'll glob inside and outside as we pull the wire through to seal it. We're going to attach this now to our Arduino, and this is an open source microprocessing board developed originally in Italy. Since it's open source, there are a lot of knockoffs that are available that are very expensive and actually work pretty well. It has a integrated development environment, if you will, in order to program it. So it's very simple, but it does give us an opportunity to actually introduce some coding. The program itself is called a sketch. The physical connection between the pressure sensor, temperature sensor, and the Arduino is just the 4 wires connected in this configuration. And here we have it actually plugged into the LCD shield, which is sitting on top of the Arduino. The Arduino connections are mirrored in the LCD shield, and so they're exactly at the same points. We will load the IDE into our computer. The program is available by just downloading it from the Arduino website. I might mention that there are a lot of really good videos available on how to use the Arduino and how to load the IDE sketch, etc. In this case, the sketch itself was created using AI. I used a Copilot. I asked it to create a sketch for the Arduino Uno and the sensor, the LCD output, and copied and pasted it right in, and here it goes. It actually worked. That was pretty cool. So we have our Arduino loaded and ready to go. And so now let's see if we can actually do some visualization then of the Charles and Boyle's law. The first thing that we'll look at is the relationship between pressure and volume. In this case, I've actually put the Arduino and the LCD in a plastic food container so that it makes it a little bit easier to protect it. And it has an external power supply. There's a lot of power supplies that are available to power the Arduino. So our initial pressure is 751.32. This is in milligrams of mercury. You can ask it in the script, in the sketch, whatever output that you want, Pascal, mercury, millimeters, however you want to do it. But anyhow, case this is in milligrams, and so when I squeeze the bottle, you'll notice that the pressure has increased to 795.75. So I reduce the volume, the pressure increased. Okay, bingo, that one worked. Let's see what happens when we do the temperature. We'll lower the temperature of the bottle down, in this case, to minus 3.33 Celsius, and our pressure is down to 990.7. In this instance, I ask it to output in hectopascal. We raise the temperature to 29.98 Celsius, and our pressure is up to 1164.05 in hectopascal. Once again, our relationship is there. We have fixed volume, increase the temperature, and the pressure goes up. So let's see if we can take this maybe a step further and look at the Gay-Lussac law, where the P1 times P2 equals P2 times T1. And I have to always remind myself that the temperature in this case has to be in Kelvin. And we're going to add data logging to this whole process then. So what we'll do is we'll prepare our experiment by taking and putting our bottle with the sensor in it in a insulated container. I have put 2 pieces of coat hanger wire across here because I'm going to fill this container with ice water, and I don't want the bottle to float up out of the container. I'm going then to attach it to the computer, and I'm going to have Excel running. Well, for our Arduino connected and our ice bottle ready to go, we can start our data logging process. We'll begin that by selecting Data Streamer. If you don't have Data Streamer currently installed on your Excel, you can go ahead and do that by going to File and selecting it for Options. There's also a lot of really good videos available on how to use this process. We'll click Data Streamer, click on Connect Device. It will confirm that our device, our Arduino, is indeed connected. We'll go ahead and start by clicking our Start Data Streaming. In doing that, it confirms that indeed our data is being recorded. Our time, a temperature in Kelvin, given that is the way that the strip was written, as well as the pressure in Pascal. Once we are confirmed that they have data streaming, we can go ahead and hit Data Record and then carry out the steps of our experiment. Once we have completed that, we can stop our data recording, at which point it will ask us to save a file, and we can do that. Okay, so now we are going to back up a step here, and that is that we have our data logging running. We're going to go ahead and put ice now into our insulated container with our bottle down in the bottom, and be logging the output from the pressure and temperature device. One of the other options, instead of using ice, is actually to take the bottle itself and put it into a freezer. So if you have a freezer available, that actually might work just a little bit better because of the fact that we can get a lower temperature than we can with ice water. Our next step then would be to heat it. First off, confirming our pressure and temperature with regard to the low temperature itself. The other aspect of it then would be to go ahead and heat the bottle. And we have 2 options here. We could pour out the ice water and then pour boiling water into the insulated container. Or in this instance, what I did is I actually placed it in the oven. I turned the oven on to about 200 degrees Fahrenheit, shut the door, and in the meantime, the data logging process is continuing all along. Now that we have our data in place, we can go ahead and look at the results. The first column is degrees in Kelvin. Here I've changed it actually to hectopascal in order to have our graph a little bit more scalable. And they're plotted, and you see that it's virtually parallel. And I selected 2 temperature points. The first one, T1, and another one, pressure temperature at T2. That's on down to the bottom of the page. With the corresponding pressures, I multiplied T1 times P2, multiplied T2 times P1, that's our formula, and here are the results. I then divided this into here, and I got the air being extremely small. So, golly, it really does work. Well, let's say if we can actually take this on to another step, and that is to look at the atmospheric pressure and altitude using the same device. Well, actually, in this particular case, it's not in the bottle. It would work well within a bottle, but in this case, you would have to take the top off, of course. But what I'm going to do is I'm going to take the device and ride an elevator. This happens to be a 5-story elevator. Basement. 1, 2, 3, 4, 5. I found a calculation sheet on the web. The address here is at the bottom. Anyhow, this has an opportunity to put the pressure at the first floor in, and this is in hectopascal. You can select whatever value units of measure you wish. I put in the pressure then at the 5th floor. The pressure is lower as we go up. Atmospheric pressure is lower as we go up. Once again in hectopascal. And I asked for the altitude difference then output in feet. And I had 55.5 feet. And that seems pretty reasonable for a 5-story building. Say maybe 11 feet or so between floors. You can actually take this probably maybe even a step further if you'd like. And that would be if you live near a high hill or a mountain, you could measure the temperature and pressure at the base and then go up the hill or mountain and measure them up the higher elevation, do the math, and come up with a confirmation at that particular point. If you do that, be sure, obviously, take it out of the car and the bottle top is off, and maybe wait about 5 minutes for it to stabilize when you take each of those 2 measurements. Some final tips and takeaways. So first off, I wanted to point out that I found this particular device to be extremely accurate. We're talking about the sensor itself is less than $5. And so in the measurement, when it was in millimeters of mercury, I used the conversion factor to inches, came out to 29.84 or so inches of mercury, which was really close to the atmospheric pressure at that particular point. The weather station is right in the backyard, so it may not be 100% correct. When we did the temperature pressure ratios, we found that indeed that worked out really well. And so I point to add, though, that when you're doing the soldering of the connectors to the 4-conductor wire, use a third hand. In this case, it's an alligator clip on a stand. Yeah, you can make one out of a coat hanger and alligator clip, but it makes that process a whole lot easier. Incidentally, the 4-conductor wire happened to be an old USB cable. I just cut the ends off and used that for the 4 conductors. Another suggestion, and that is to actually change it from a juice to a juice bottle from a soda bottle. The juice bottle is much stronger. The plastic's a lot thicker. A soda bottle really deformed after squeezing it, and also when heating it with the hair dryer, the shape just distorted. One thing I discovered, and that was that hot glue melts at a relatively low temperature. It's about 130 degrees or so for the standard hot glue. And so when I put it in the oven, as the pressure was coming up, the glue melted and I had a blowout. So we had to call off the experiment at that particular point. So maybe a good substitute would be using a two-part adhesive epoxy and sealing the opening. I really haven't tried that yet, but that may be a solution. But keep in mind, if you're going to do it in the oven, make sure that you keep the door closed because there is a possibility that that bottle could explode, and we want to keep safety in mind. And then, so the other thing is, if you are going to use ice water and boiling water, is to use a larger container. The container that I used was a pharmaceutical shipping container, and it was relatively small volume in relationship to the area, the volume that the bottle took. So it didn't leave room for a lot of ice water. So I suggest using just an inexpensive cooler if you're going to use the water and boiling water and ice. Finally, I want to point out that in changing the sketch in Arduino is really easy. Once you have the sketch loaded, if, for instance, if you want to change the output read from Celsius to Fahrenheit, it's merely just to add the conversion factor in, substitute, add it right into here, change this from a C to an F. When we make these changes, always make sure that you keep the semicolon in place because that's the instruction for the program to move on to the next line. Also, as far as the frequency of reads, this is output is unit of measure is in thousandths of a second, and so if you would like to go ahead and change that to read at 1 second intervals, you just change the value to 1,000. And I would recommend that for the data logging. 2 seconds works really well for the LCD because it gives time for the screen to refresh between each reading. But for data logging, it might be advantageous to have more output. So with that in mind, we will go ahead and thank you for your attention and give you an opportunity now to ask some questions.
Thank you, Ken. We have some comments in the chat, but if anybody wants to ask any questions, feel free to unmute.
I just have a comment I'll share, Ken. That's amazing, the affordable price and the accuracy of the data that you're able to get with that sensor. Having taught gas laws myself for more than 2 decades, we always did it with relatively expensive demonstrator units that you get from the supply houses. That would involve an analog pressure gauge and a giant syringe or something like this. But this is more affordable, and you could let students do it in a lab group with teams and explore the relationships for themselves. I think it's just amazing. What a cool device.
Well, thank you, because you can do the whole thing for about $20. So.
Yeah, it's really astonishing how affordable it is, and I'm impressed that it's sensitive enough that you can see the pressure difference in a 5-story building with such an inexpensive device. It's incredible. I was thinking a little bit, having taught high school for a number of years, like if I was going to implement this with students, it would be challenging for me to get access to an oven to put that in. I would have had to, do some favors for some of the home economics teachers to let them loan me their kitchen for a day or something like that. But I know a lot of physical science teachers have access to solar ovens. That was an experiment we always used to do. Looking at heating of black objects and silver colored objects, and looking at both irradiance and thermal absorption. And if you had a solar oven, that would be something you could take outside relatively easy as an instructor. Pop that bottle in there, and we used to get temperatures of 200 to 300 Fahrenheit all the time out of our solar ovens. So this would be a good outdoor experiment to do with students as well.
Right. I think one of the things there again is to keep in mind is that as you raise the temperature, maybe using the hot glue would be best. You can have a high temperature hot glue, which would melt at a little bit higher temperature, but having that safety release would be maybe a good idea to have. But by the same token, if you don't have a freezer and oven available, the ice water and the heated water gives a pretty good temperature range as well.
Ken, I don't really have a question. I just want to make a comment. I have been to a lot of these, and they're always very enlightening. But frankly, this has been one of my favorite presentations I've seen. I just want to say thank you for coming in and taking time to present this. This is just super helpful, super applicable. I think you did a fantastic job kind of painting the picture of how to do it. Just thank you very much. This made my day.
Well, thank you. Appreciate that.
Ken, I'm curious, do you have either a set of data or a parts list or procedure that you've written up for this that you might be able to share with our audience at all?
I will certainly pass that on to Gabby, and so that to make that available.
Oh, that would be great.
This is Gabby here. When I post the recording, I could actually add the parts list next to it. So it's available with the recording.
So I have a question. I don't know if you can hear me.
Yeah, we
Okay,
hear you.
yes.
Go ahead.
Oh, so I was just wondering if you changed the gas that was in the bottle, so like carbon dioxide or something else, what helium or something, is this going to change the readings? Obviously it would, but I mean, how does that reflect?
Well, I think the challenge would be actually charging the bottle with a different gas other than just air. But it could, but our ratios ought to be consistent. There'll be different numbers, but the ratios should be the same.
Yeah, as long as the other gas you introduce behaves as an ideal gas, you should
Right.
discover the same results. I think what you'd have to do is probably invert the bottle in some water and then collect the gas by bubbling it up into the bottle, you know,
Right.
from a tank of oxygen or a tank of nitrogen or something like that, so that you could, you know, fill the bottle with something other than just air. But I can imagine that, you know, being kind of a cool experiment to do, just to show that it's not just applicable for air, but for any ideal gas.
That's an excellent suggestion. That was one of the things I discovered with this. There was a lot of things that you can do, as it says. It started with just the simple explanation of the gas laws, and then added on the ride in the elevator, and so there's more things that you could do with it as well.
Yeah, Ken, how many years have you been tinkering with this?
Well, I believe it's actually 7. I went back and um, I know that you've had encouraged me to do this a long time ago, but we finally got it done. So thank you.
Well, I know this was something you wanted to write up and publish too, because it is pretty cool. So if we could put that out on the creative, our team would like to build one of these ourselves, right? I know there's a lot of
I
people
can
that
I
would
can
like
see
to-
this being a great publication either for ASCE side of engineering education or Journal of Chemistry education. You know, both engineers and chemists all teach gas laws as part of their undergraduate education. So I could see this having a lot of interest. I'm ready to build one myself, Ken, because I want to recruit one of my friends who's a pilot to take me in an open cockpit Cessna and fly with this thing.
There you go. There you go. Just take your laptop along and plug it in, and you're getting this data log. And using that Excel, works really well. It's an easy way to do the data logging.
I'm curious, how much was involved in writing the code to program the Arduino?
Well, actually, you can literally use AI and just tell it what you want, and it's amazing that most of the time it'll actually work. So
That's brilliant. What a cool world we live in.
it is, and they're all there's nothing unique about actually using this particular BPM 280 sensor. There's a lot of sketches written for that, so that's not hard to find one. As I said, it's relatively easy to change the output, or if you want it in Kelvin, or you can put the conversion factors, those types of things right into the script itself.
Great. Thank you all for will be recorded at the site and get some more instructions from Ken. We'll publish them as well. Our next webinar series the announcements will be in the fall for next spring. So, Gabby, what else am I forgetting?
We will also have coffee hours and a fall series of webinars, and we will get announcements out about those probably midsummer. And there'll be more information coming out about high tech, but we want to thank you for joining us and have a great weekend.
Thank you all.
Thank you,
Thank
Ken.
you, Ken.
Really
It was
enjoyed
really
it.
great.
Thank
Yeah.
you, Ken. That was fantastic.
Thank you.
Yeah.
Great job.
Yeah. Thanks everybody for joining us.
Have a good weekend, folks.
You too. Bye.
Bye.